Swayam Prabha. Digital India. Educated India.
Hello, welcome to the course on comprehensive view of speech processing, and today's lecture is 23rd in the series, and today we are going to discuss about the linear prediction analysis of a speech like in practice. So, it means that actually so far we discussed about the various aspects of linear prediction analysis of a speech, starting from like the basic modeling of the LP analysis on the speech, then both the generative and analysis model, then how to predict, how to compute the efficient or like the effective linear prediction coefficients for a given speech frame, right. And afterwards we discussed about like how when you apply a linear prediction analysis of a voiced speech frame, so what you can able to observe, and for unvoiced speech what can be observed, right. In the process of linear prediction analysis of a speech, so how the error used to be, what will be the error signal, like how the error signal, the nature of error signal in the context of voiced speech and unvoiced speech, right, and what is the effect of this linear prediction order, nothing but the number of prediction coefficients that can be considered on the error signal and as well on the spectral envelope of the vocal tract system. So, all these aspects we have discussed in the preceding lectures, and as well we also discussed about like how do we can able to derive the information, or we can say that how do we can derive the spectral coefficients or the information from a speech signal, either by using linear prediction analysis or by using spectral analysis. And in this context we also discussed about how do we separate because the speech signal is, you can say that it is a combination of both the vocal tract information as well as the excitation source information. That means both the components are present in a speech signal, and how do we separate these two components for better analysis, because for certain cases in view of discriminating the various sounds or discriminating the various speakers and all, so it's maybe better that actually if you can able to separate these two components, and by using these two components separately for discriminating the either sounds or speaker specific information or a language specific information, it may give you a better information. Otherwise, if you combine, then some of the information may be with the overlapping or with the combination, it may be it may not provide you the desired discrimination information. So, that way we can able to split, or we can able to how do we divide, how do we separate the components of vocal tract and excitation source information. In that context we discussed about a capstem analysis. So, by using the capstem analysis we can observe that actually the vocal tract component and excitation source components can be extracted, can be separable in the capsule domain, and in that context as the capsule domain provides these two information in a separable way. And not only that, we observed that the coefficients are in a capsule domain, the features are more robust compared to directly using the linear prediction coefficients. So, that way we have seen that how do we extract the capsule coefficients and how do we extract the linear prediction capsule coefficients from the linear prediction coefficients. So, all these aspects we have discussed. So, when you are discussing about extraction of capsule coefficients or capsule features, what we observed that these capsule coefficients are sensitive, the lower order capsule coefficients are sensitive to spectral envelope, and whereas higher order capsule coefficients are sensitive to noise. So, for that purpose, to make these capsule features to be robust, so we scale the capsule features by appropriate weighting by superimposing the appropriate weighting characteristic or weighting plot, or this one that is known to be the outcome of that is the weighted capsule coefficients. So, which are like more robust and which are not sensitive to like either speaker specific content or the other noisy content like environmental variations and so on. And finally, to capture the dynamics of vocal tract shape, we have also included the time derivative capsule coefficients, which are known to be the velocity coefficients or acceleration coefficients, also known to be delta and delta delta and so on. So now we will try to see that actually now here in this class we will see that. So just we will take practically the speech signal and then we carry out the LP analysis on that. We will try to extract the LP coefficients and use that LP coefficients for analyzing the like the spectral envelope or the error signal, and we also see that how the error signal varies with respect to the prediction order. So all these aspects whatever we discussed so far. So let us see in a MATLAB environment, in a lab environment, when you try to do all these things from taking the segments of speech signal, and if you work and if you perform the LP analysis over that, how the things used to be, and so those aspects we will try to discuss today. And once we complete that, then afterwards we will move to the next topic known to be the vector quantization. So first let us see the linear prediction analysis of a speech in a MATLAB lab environment. So I think here in this we will carry out this the following tasks here. And altogether it is a linear prediction analysis. The tasks that will carry out here in this study are like, so first we will capture a speech segment of, for example, 200 milliseconds, which is a voiced segment, and another segment of 200 milliseconds of unvoiced segment. Then afterwards we will try to compute the spectrum and the inverse spectrum. That means nothing but we will try to compute the short term spectrum and its inverse spectrum for 14th order LP analysis, and then we will carry out all these things, like we will find out again the spectrum and inverse spectrum for a 14th order LP spectrum for unvoiced speech. For a voiced speech we will take the vowel segment of A. For unvoiced segment we will consider the frication sh. Like then we will see the LP residual for both voiced and unvoiced segments, how it used to be. So here we will see that first we capture the voiced and unvoiced speech segments of 200 milliseconds, and from that we extract the 20 millisecond segment with which you can compute the spectrum. First we will compute the normal short term spectrum using FFT, and afterwards we perform the LP analysis of 14th order, and then we will compute the 14th order LP spectrum. We will see that how the LP spectrum and the normal spectrum, how they correlate, right. And similarly the same thing we will perform on the unvoiced speech segment. Then we will examine in the analysis process, we will try to see that what will be the error signal in the context of voiced and unvoiced segments. Here the error signal also known to be LP residual that we discussed, like we have like we can call it as either LP residual or the error signal or the excitation signal, all are one and the same. Then afterwards we will see that actually the autocorrelation function for a signal, normal speech signal, and its LP residual for a voiced and unvoiced segments, how it used to be, right. And then we will try to see that the LP residual for a voiced segment, and then from that we can able to derive the glottal pulse signal also, a glottal signal by integrating the LP residual. So all these things we will try to discuss, and finally we will see that how the LP spectrum, by varying the LP order, by varying the different LP orders, how the LP spectrum varies, right. So from that we can come to know that actually what will be the reasonable LP order for the analysis of voiced segments, and we will also see that how the normalized error varies with respect to the LP orders for both voiced and unvoiced segments. So all these things we will discuss one by one with the appropriate plots. Here first we see that here this particular plot corresponds to a voiced segment for a 200 milliseconds, and here we can directly record through a microphone, and then we can from that we can segment this 200 milliseconds, and then we can plot it, right. So for that the commands that are required will be shown later, and this is the voiced speech segment of 200 milliseconds, and this is the unvoiced portion, the unvoiced speech segment of 200 milliseconds. And here as I mentioned that the voiced segment is from the vowel A, it was taken from the vowel A, and for unvoiced segment, this was the segment that was taken from the frication sa, right. So, this is a voiced segment and this was the unvoiced segment, right. And then afterwards, now we will see that we will compute the spectrum. So, for computing the spectrum, we cannot take the 200 milliseconds, because the 200 milliseconds means where during that period the signal characteristics will get vary. So, therefore, to analyze the characteristics in a case of steady manner, so what we need to do is that we will take a short segment of the voiced segment as well as the short segment of the unvoiced segment. So, therefore, for that purpose we are taking a short segment of voiced speech, that is around 200 samples. It is nothing but 20 milliseconds. It is nothing but 20 milliseconds, because here the signal is sampled at 10 kilohertz. So, therefore, the 200 samples is nothing but 20 milliseconds. So, we considered 20 milliseconds of a speech signal, right. And so, using these commands, the MATLAB commands, you can able to extract the 20 milliseconds of a speech segment, right. And as we know that, as we have mentioned, that to perform any analysis and all, it is better to pre-emphasize the speech signal, right, because we have seen that when you are computing the linear prediction capsule coefficients, what we mentioned is that the first step need to be performed for any feature extraction will be pre-emphasize the speech signal. So, with that the high frequencies will be emphasized. So, due to that the all formant frequencies will come to the same level, similar level. Otherwise, what happens, the first formant will be very dominant, right. So, with that the other formats, the extraction of the accurate extraction of other formats or knowing the other formats will be very difficult. So, therefore, first you pre-emphasize the speech signal, and in a time domain the pre-emphasis or this first order linear filter, FIR filter, can be implemented by simple difference operation. It means that taking a successive difference between the samples, it is nothing but pre-emphasizing the speech signal, and then we take a pre-emphasized speech signal, and in that we will take 200 samples of it, and then we will compute the spectrum. So, for computing the spectrum, as we have mentioned that after performing the pre-emphasis, we have to take a frame. Here you can see this statement A equals to diff A is nothing but pre-emphasizing the whole speech signal of 200 milliseconds, and from that we are taking a 20 milliseconds, is nothing but extracting the 200 samples from it, right. And this becomes is nothing but framing, right. It is nothing but framing, and after once you take a frame, here we know that this particular frame is, right, this particular frame where the edges of a frame are suddenly truncated. So, to avoid that we do the windowing. So, you can see here in this step we perform the windowing, that means whatever the frame we have considered, that frame is multiplied by Hamming window here. So, we will get the windowed version of the frame. So, with that the edges will be tapered off, so that the distortions will be minimized. So, this is the windowed speech signal. After you compute a windowed speech signal, the next step is that we perform, because to analyze, to see the spectrum in a normal spectrum, right, short term spectrum, we apply the FFT. See that we are applying FFT, and for applying the FFT, the arguments that are required will be, first thing is the signal is required, and we also specify that how many points, like the n value, like how many points the FFT has to be given as output. So, here the 1024 we have taken. So, therefore, by using FFT you can get a spectrum, like for a 200 millisecond speech signal, right, 200 sampled speech signal, or sample speech signal is nothing but 20 millisecond sample speech signal. After Hamming windowed, then we applied the FFT over that with the 1024 size, the number of the coefficients. So, with that we will get a spectrum, and from the spectrum, the spectrum is complex spectrum, right, it contains both magnitude and phase. So, here we will focus mostly on the magnitude part. So, therefore, taking the modulus of it will give you the spectrum. We are taking the squared spectrum, right, the power spectrum, that is nothing but the spectrum multiplied by itself and take a absolute, the modulus value, and then afterwards we will apply a logarithm over that. So, this is a log magnitude spectrum we can able to compute, and now we are plotting that. So, that way similarly we are computing LP spectrum also, we are performing a LP spectrum also. So, for performing LP spectrum, so it is nothing but we have to calculate to plot the LP spectrum, what we need the LP coefficients. So, to extract the LP coefficients from a speech signal, we have a MATLAB function where LPC with the two arguments, one is the speech signal and other one is the order we have to specify. Here we mentioned order as 14, right, and the speech signal, the 20 millisecond speech signal has been passed as one argument, and the MATLAB function is LPC. So, it derives the AKs, that means linear prediction coefficients. So, once the linear prediction coefficients are available, then using the filter function, you can say that for the QZ is a filter function. With that, by providing the numerator and denominator, here 1 comma AK. So, 1 is nothing but the numerator part and the denominator is AKs, because here in this filter is like a all pole filter, right. So, therefore, the numerator there is nothing and the denominator we have set of AKs. So, by passing these two arguments, it computes the LP spectrum, and again from the LP spectrum we will compute the LP spectrum is again it is a complex one. So, therefore, to get a log magnitude of the LP spectrum by using these two functions you can able to, then we can able to plot the LP spectrum also, right, by using this particular MATLAB commands. And now, if you look at the spectrum, and similarly the inverse spectrum also you can do that, right. Once the LP coefficients are available, then here you can see earlier the filter, you can see the function will be FREQZ, it is nothing but filter function, and here earlier we had given 1 comma AK, that means 1 in the numerator part, AK is in the denominator. So, now in the inverse spectrum, so they are reverse, that is the reciprocal of it, right. So, in the numerator we have AKs and the denominator there is nothing, only 1, right. So, therefore, this is the inverse filter, and then by with the inverse filter we will get an inverse LP spectrum and then computing the log magnitude spectrum of it. And now, what we got? We got the we have taken a 20 milliseconds of a speech segment, and then we performed the FFT and we performed the LP analysis, linear prediction coefficients, and then we computed LP spectrum and its inverse spectrum also. And now, if you look at here, whatever the obtained results, if you plot it, you can able to see here. Here you can see the first one is the 20 milliseconds voice segment. Here we have taken this voice segment from the vowel A. So, this is a 20 milliseconds time domain signal, right, from a voice segment it was extracted. And next this is, right, you can see here this is nothing but the FFT spectrum that was computed, and here from the FFT spectrum we are not interested in the phase information. So, therefore, we extracted only the magnitude part of it. So, this is the magnitude part 20 log like mod of S of omega, it is nothing but the log magnitude spectrum. So, if you compute the log magnitude spectrum, you can see the FFT spectrum or the speech spectrum looks like this. And here you can see from here, since as I mentioned that since this is the spectrum for the entire acoustic signal, speech signal, which contains both the spectral details of excitation source and as well as the spectral details of the vocal tract system also, right. So, the vocal tract system provides you the gross resonances. You can see these are the resonance frequencies, the peak frequencies at a lower end, and this is the dominant frequencies maybe at a higher end, right. And on top of it, the excitation, spectral characteristic of the excitation is superimposed on it, because this is a periodic signal or extracted from a vowel segment. So, therefore, the related the periodicity related information is also superimposed on it. So, therefore, the ripples whatever you observe over here, these are due to the excitation source, and then the gross envelope is corresponds to the vocal tract. So, therefore, this is a short term spectrum or the FFT spectrum of a speech signal, which contains the information, spectral information of both excitation as well as the vocal tract information. And now, the third plot here you can able to observe here. So, this third plot is nothing but the LP spectrum. So, we have seen from the same speech signal, first we derived the LP coefficients with the order 14. So, we got a 14 LP coefficients, that is nothing but 14 AKs, and now you plugged in that 14 AKs in the synthesis filter, that is 1 by AK all pole filter, and as well as all zero filter, that is inverse filter also. So, then if you the synthesis filter, that means if you put it in if you place it in the all pole filter, and then if you compute the LP spectrum and for that LP spectrum, if you compute the log magnitude spectrum and if you plot it, you can able to see the LP spectrum for a 14th order on this particular speech signal. It looks like this. If you look at here, the plot of this LP spectrum almost resembles like at a gross envelope of the short term spectrum, Fourier spectrum. You can see the short term Fourier spectrum like this, and here the LP spectrum captures the dominant frequencies in the speech signal, right. So, here you can see the dominant frequency here, the peak that was captured here and another one is captured over here. These are the dominant, and then there are other ones also. If you keenly observe, you can see that one, right. But there are 3 dominant frequencies that you can able to observe, one over here and another one here and another one here. So, this almost like matches to the true spectrum. The true spectrum means on a speech signal directly, if you apply FFT, whatever the spectrum you will get, that is the actual spectrum of a speech signal. It contains both the information related to excitation as well as the vocal tract. But the LP spectrum, it captures only the information related to mostly the vocal tract information, because the linear prediction coefficients, and just we plugged these linear prediction coefficients in the all pole filter. So, therefore, whatever the spectrum you observe as part of it, it contains only the information about the vocal tract information, right, vocal tract. And if you look at this, the broad characteristic or the envelope of this the LP spectrum and the envelope of the gross envelope of the normal spectrum, the normal speech spectrum, they observed to be like they are almost like they are very close, right. Here you have a dominant frequency, here dominant frequency, here also you can able to see like the peaks here also and here also at a very gross level, and the other places the spectrum is more or less flat, right. So, this is the LP spectrum for the all pole filter, right. And then if you analyze the inverse filter, if you analyze the LP spectrum for inverse filter, this is nothing but because this is LP spectrum from all pole filter, that means 1 by A of Z, and we have taken the same LP coefficients and we formulated as all-zero filter as an inverse filter. So, for the inverse filter, whatever the LP spectrum you observe here in case of the all pole filter, you just see the reciprocal of it. That means, wherever the poles are here, you can see the corresponding zeros over here, because the same LP coefficients we are using earlier, that those LP coefficients are part of the all pole filter, it is nothing but a polynomial in the denominator. Now, here the same LP coefficients in the numerator part, right, an all zero filter. So, therefore, you will get a corresponding zeros wherever the existing poles are, earlier poles are there, you will get the zeros in the same locations, and therefore, this particular plot will be exactly the reciprocal of this. So, this way you can able to, from a given speech signal, you can able to derive the normal the FFT spectrum, like the spectrum for the whole speech signal, and this is the spectrum for the vocal tract system, and this is the spectrum for inverse filter. Sorry, okay, yeah. So, next we move on to the next part of the analysis. You can see that from the segment of voices speech of R 20 milliseconds, and the B is nothing but short time spectrum, and LP spectrum and inverse spectrum. And now we carried out the same analysis here for the unvoiced speech, right. So, here this is your 20 milliseconds speech signal, sorry, unvoiced speech segment, because here in case of voice speech segment, where you can see that the vocal tract shape is varying. So, because of that, actually we considered just 20 milliseconds of a speech signal, and here also we consider, for the sake of the same thing, here we consider the 20 milliseconds. Otherwise, here you can able to consider even a longer segment also, but here we consider the 20 millisecond segment of unvoiced speech, and again this is taken from the fricative sound sa, right, from sa we have taken this particular segment, and for this particular segment, the same way whatever we discussed earlier in case of voice segment, the same analysis has been carried out. So, for this 20 millisecond unvoiced speech segment, you can see how the signal is fluctuating, it is very random in nature, right. Earlier you can able to see some periodicity, here it is a random in nature. So, therefore, if you compute the spectrum for this, right, this is almost like very noisy. So, if you compute a spectrum using the FFT, right, you can see the spectrum will be almost like a flat, you do not see any dominance, you do not see any dominance, right. The spectrum is almost like a very flat, and here as this is on the spectrum is computed on the speech. So, therefore, you can able to observe the ripple, right, and then here the same thing here instead of FFT, if you perform by using LP analysis with a 14th order, you can able to see the LP spectrum in view of all pole filter. You see that the spectral envelope of LP analysis, right, offers you this envelope, and this is almost similar to this one. You can see, if you see the gross envelope, right, is almost matches to the LP spectrum, the envelope of the LP spectrum, right, and this is for the like the generative filter or for synthesis filter, right, and this is the inverse filter of it. So, therefore, in the inverse filter, if you look at the spectral envelope, it almost like it is just observed to be a very reciprocal of it, because these two are related by the same set of LP coefficients, but the third plot is generated from the all pole filter configuration, and the fourth plot is generated from the all zero filter configuration, right. So, you can see that the only observation here to be noted here is that this is unvoiced segment. So, therefore, for unvoiced segment you do not see any dominant frequencies, like the spectrum will be more or less flat, the spectrum is like more or less flat, that is what the observation need to be. And in the case of LP analysis also, you can able to see these things like properly, these things you can see here and all. So, like it almost like approximates the spectrum whatever you got it here. The next thing to be like LP residual for voiced and unvoiced segments, LP residual for voiced and unvoiced segments. LP residual is nothing but as a error signal, right. We have also mentioned that the LP residual is nothing but in the process of LP analysis, whatever the signal which is not predicted by the LP analysis is known to be LP residual, because that is what the remaining as error between the actual signal versus predicted signal. The remaining parts are predicted properly, but there are certain information which is not predicted from the LP analysis, through the LP analysis, known to be the LP residual or a linear prediction residual, right. So, here for computing linear prediction residual, so what filter need to be done? That means, for computing the error signal from a given speech segment, what kind of filter that need to be done, that need to be used, right. So, we have seen that in case of synthesis filter, the filter transfer function is 1 by A of z, right. For a synthesis filter, the filter transfer function is 1 by A of z. So, for synthesis filter, the input will be the excitation and output will be the speech, whereas for the analysis filter, that means to compute the LP coefficients, right. So, the input will be the speech signal and the output will be the error signal, So, therefore, for that you can say that the residual signal is the error signal is nothing but this is the output, and the filter transfer function will be all zero filter, right, all zero filter. So, therefore, for a filter transfer function there are three attributes will be there. The first two attributes corresponds to the transfer function, and the third attribute corresponds to the signal. The third attribute corresponds to the signal. That means, there are three attributes any filter function will take. The first two attributes corresponds to the transfer function, related to transfer function, and the third one is the input. Third one will be the input. So, here you can see the AK are in the numerator part. The first one attribute corresponds to the numerator of a transfer function, the second one corresponds to the denominator of a transfer function, and the third one is the signal, the input signal. So, here the first part is nothing but numerator, the A case, because we know that the analysis filter is the all zero filter. So, therefore, the coefficients whatever that need to be, so those coefficients has to be given as the numerator part, and the denominator there is no polynomial at all. So, it is simply unity, and then the signal that need to be passed will be the speech signal, So, the outcome will be the LP residual, right. So, with this MATLAB function you can able to compute the LP residual from the given speech signal with the computed LP coefficients, because these LP coefficients we have computed earlier, right. In the analysis phase we have computed LP coefficients from the given speech signal, right. So, we have seen that when you are deriving the LP spectrum, first we computed LP coefficients, then from the LP coefficients we derived the LP spectrum and we plotted, we have seen how the LP spectrum look like and how the short term spectrum looks like and all. And now we got the residual signal, or this one the error signal, and now we will see we will plot the residual signal and we will see that how it looks like, because the outcome of a filter will be complex signal again. Please note that the outcome of a filter is nothing but a complex signal, and from this complex signal we are interested in the real part of it, or this one. So, therefore, we are taking a real part of the residual signal and plotting that. And if you look at here, you can see this is the configuration of the filter, speech signal, and then we are giving to the inverse filter, that is nothing but all zero filter. Output will be the error signal or the residual signal. And now if you look at you can see, yeah, this is my speech signal, right, the 50 milliseconds of speech signal from a voice segment, right, from a voice segment. And if you compute the linear prediction residual for this particular speech signal, right, how do we do that? We use the filter, where the filter will be all zero filter, and then the numerator consists of the A case, right, and then we pass the speech signal, this particular signal, through that filter. Then the output will be observed like this. You can see, since it is a periodic segment, right, as we have mentioned from a voice segment, right. So, the error will be, as I have mentioned that in the class, the error you can able to observe, the maximum error you can able to observe at a glottal closure instant, right. So, that means, because this is a periodic segment, vowel segment. So, this vowel segment is produced due to vocal folds vibration, right. Whenever the vocal folds closes, you can have a sudden narrow pulse will be, or narrow impulse will be generated, and that will be propagated through the oral cavity, and then the oral cavity response nothing but the resonances will be superimposed on that. That way you can able to see the speech signal something like this, and this is the linear prediction residual, or you can say that this is like kind of the excitation signal corresponds to this particular speech signal, right. So, this is the, because at this point the glottal closures takes place. So, therefore, the behavior of a speech signal is also very different, and because the narrow impulse will be generated, and this is not predictable. So, that is the reason that in the analysis phase, right, the remaining parts are predictable, but at a glottal closure phase where there is a sudden impulse will be generated. So, the impulse is nothing but in a very small instant of time the signal behavior changes very rapidly, that you cannot capture from the previous history or the preceding samples. So, that is where you can able to, it leads to the maximum error at the glottal closure instant. So, that you can able to observe at every period, each period, because whenever the glottal closure takes place, so that part is not predictable. So, therefore, if you look at in this speech signal, so the corresponding glottal closure instants, you can see a maximum error, you can see here and all, see that error will be maximum, right. And if you look at the magnitude of a speech signal versus the excitation signal or the error signal magnitude will be less, obviously, right. The speech you can see here, it is ranging from -1 to +1, whereas the corresponding residual will be ranging from +0.2 to like -0.4, and here you can able to observe this maximum error is mostly at the instant of closure. Only at 1 or 2 samples you can able to observe this error, and the rest of them the error is confined to very small range, very almost like +0.1 to -0.1, right. Only at the instant of closure the error is almost touching to 0.5, right. So, this is about the error or the LP residual for a voice segment, right. So, this is what we discussed in the class, and now if you can able to do it in a lab with appropriate MATLAB commands, you can able to see clearly that at the glottal closure instant you can able to see the maximum error. You can see the rest of them, the error is almost like very close, it is like you can say that 0.1 or even less than that, like a 0.05 to -0.05, it is varying, right, very limited range. But during at the instant of floater closure, it has a maximum error. And then if you look at this, plot C is nothing but the unvoiced segment. We have taken 50 milliseconds of unvoiced segment, and here also if you try to determine the LP residual linear or error, or the error signal corresponds to this particular unvoiced segment, you can see the error segment will be this one, and you can see the error segment is varying, right, you can see continuously it is varying and all. And unlike here, you can see the error segment is the error is very small, and here you can see the error is a bit higher, right, and it is continuous, like in all the places the error exists and all. Because it is unvoiced segment, you can see there are lots of fluctuations on this signal, and that makes the signal to be like very random in nature. So the correlations between the coefficient between the samples are very less, they cannot predictable. So that is the reason that you can able to observe the prediction error, bit higher prediction error and all, right. So we can able to see the difference between the linear prediction residual of a voiced segment versus the unvoiced segment and all, voiced segment versus unvoiced segment. And you can see the unvoiced segment, you can see the signal is almost fluctuating very close to 0, but still you can able to see the error will be almost of the similar magnitude of this. Whereas in the case of voiced speech, the signal fluctuations are very high, like a -1 to +1, and whereas the error is about 0.05, around plus or minus 0.05, right. And now you can see the next thing what here what we are the analysis what we are carrying out here is that we have taken a voiced segment of 20 milliseconds, right, and if you apply autocorrelation on this directly, because this is a periodic signal. So if you apply autocorrelation, the autocorrelation function is a periodic, right, because we know that the properties of autocorrelation function, the autocorrelation function is asymmetric. You can see that this is a speech segment, right, voiced segment of two periods of 20 milliseconds, and if you apply autocorrelation on this, the autocorrelation length will be twice of this, because the signal length is 20 milliseconds. So if you perform autocorrelation, the autocorrelation signal will be double to the size of the speech signal of the size of the signal, right. It is a 20 milliseconds. So if you observe the autocorrelation coefficient, autocorrelation signal, it is 40 milliseconds, right. And here you can see that the autocorrelation will be maximum at a 0 shift. That means here you can see because here the plot is made from 0 to 40 milliseconds, but otherwise if you strictly plot, the plot will be like it starts from 0 here and plus 20 milliseconds and minus 20 milliseconds, right. So but here for plotting these, I have made the scale as 0 to 40 milliseconds. So therefore here this 20 corresponds to shift 0, and this 20 corresponds to this type 20 milliseconds corresponds to a positive shift, and this is corresponds to negative shift. And you can see that the autocorrelation signal is symmetric with respect to the center, with respect to origin 0th shift. At the 0th shift you can see the maximum correlation, right, because the signal is correlated with itself without any shifting. So therefore the maximum correlation is observed. It is nothing but the signal energy, whatever the total signal energy, because when you are multiplying the signal with itself without any shift, it is nothing but each sample square is observed, and we are taking sum of those sample squares. It is nothing but its energy of the total signal, right. So that is the reason that at a 0 shift the correlation will be maximum, and afterwards you can see that correlations are reduced. And here since the signal has the correlations, samples are correlated, so therefore when you perform autocorrelation, you can able to observe the reasonable correlation values, right, at a periodic intervals. You can see here the next peak will be here observed to be here, and along with this peak you can also observe there are other peaks also. These peaks are also almost very close to this peak, but here if you clearly see, you can able to see a maximum peak other than this center will be this one, but here this peak is also almost very close to this one, right, but it is smaller than this one slightly, but it is very close to this. So because the reason is that here the signal has a correlations, right, and because of that you can able to see the autocorrelation function, it is a periodic, but at the same time here you can see the peak here is almost close to the, there are other peaks also will be there. So, in this context, if you by using this autocorrelation function, computing the periodicity or computing the, you can say that the period of the signal will be difficult, because this peak is almost close to this one. So, therefore, the accurate estimation of the pitch or accurate estimation of pitch period from this will be bit difficult, or it may leads to sometimes erroneous results also, right, because the signal has a correlation. So, if we perform autocorrelation analysis directly on a speech signal, so that leads to like some spurious peaks, and these peaks will be almost competent with the desired peak. So, therefore, like detecting these peaks will be bit sometimes leads to error. So, therefore, that leads to erroneous estimation of periodicity, erroneous estimation of pitch. Whereas, instead of performing the autocorrelation analysis on a speech signal, if you perform on the residual signal, because this is LP residual corresponds to this voiced segment. So, if you perform the autocorrelation analysis on this LP residual, so this is LP residual, we know that how to extract the LP residual from a speech signal, right. So, by using inverse filter you can able to get the LP residual. On this, if you perform autocorrelation, you can see the autocorrelation signal looks like this, where you can see at the center you will get a maximum peak, right, at the center you will get a maximum peak, and at other places you do not observe any significant peaks. There are some fluctuations are there, but there is no significant peak corresponds to this particular peak, because this is my desired peak and afterward this is my desired peak. And whereas here the signal is fluctuating, but the desired peak stands alone, stands still, like, because this is a very significant compared to the other signal fluctuations. So, therefore, by performing autocorrelation analysis on the LP residual, you can able to decide, or you can able to detect the periodicity of a signal very effectively, very accurately, without any errors. So, you can see this is the autocorrelation function for the given signal, right. This is the LP residual, and if you perform autocorrelation on this, you can able to see the signal will be symmetric and the peaks are very clear and significant, and if you can compute the distance between the center peak to this first peak, it is nothing but period of the segment and all. So, that way you can able to compute the period of a segment without any ambiguity, and so therefore, accurate estimation of pitch is possible by performing autocorrelation analysis on the voiced segment, on the LP residual of a voiced segment. So, this is one important observation. So, for the same thing, if you carry out the analysis on the on the unvoiced segment, suppose this is your unvoiced segment of 20 milliseconds, right, and if you perform autocorrelation analysis, you can able to see that this is the maximum peak and you do not see any other significant peaks, right, you do not see any other but still you can able to, because of some fluctuations or something, you can able to see some peak, and with that you may doubt that the given segment is periodic, because you can see a similar thing is observed over here. So, because of that you can able to see the peak over here, right, see the peaks here, peak here, but this is not a reliable peak, because that is the reason that if you perform autocorrelation directly on a speech signal, sometimes it may leads to error, and sometimes not only that, the accurate estimation of periodicity or detecting whether the segment is voiced or unvoiced will be difficult because of this ambiguity. So, to avoid that, instead of performing autocorrelation analysis on the speech segment, if you perform on the LP residual of it, then you see that this is unvoiced segment. For this, the LP residual is this one, So, on this LP residual, if you perform autocorrelation on this LP residual, you can able to see the outcome, the LP residual, the unvoiced segment, unvoiced LP residual autocorrelation function look like this. You can see only the peak at the center, because since we are performing autocorrelation, peak at the center means the signal multiplied by itself, you will get total energy. So, you will get a peak at the center and you do not see any significant peaks, rest in the rest of the signal. So, it means that by analyzing this, you can see that if you perform autocorrelation function and if you see the peak only at the center and you do not find any significant peaks in the signal, it means that the segment that you considered, the segment you analyzed, will be unvoiced segment, or you can say it is a noisy segment. So, but that you can able to make it very clear when you perform autocorrelation analysis on the error signal, on the LP residual signal of this particular speech segment, right. So, this is that is the reason that when you are estimating the pitch, so usually we do not perform autocorrelation on the speech signal directly. Instead, we will perform autocorrelation on the LP residual of a speech signal. So, from that we can come to know that if the autocorrelation function is a periodic and peaks are observed other than the center, it means that it is a voiced segment, and if we do not observe the peaks other than the center, it means that it is unvoiced segment. It is a unvoiced segment. So, that way you can able to detect whether the segment is voiced or unvoiced. If it is a voiced, we can also compute the periodicity of that particular segment. So, the next we move on to the generation of a glottal pulse. So, for generation of a glottal pulse, we can see that, so this is your speech signal, and if you perform LP analysis, this is your linear prediction residual corresponds to this signal, and from the linear prediction residual you can also compute the glottal pulse or a glottal waveform. So, it is nothing but simply if you perform the integration, or it is nothing but if you apply a linear low pass filter through this. So, whatever you will get, it is nothing but a close approximate of glottal pulse waveform, glottal pulse waveform. So, here this glottal pulse waveform, what it indicates over here is that here this is the open phase and this is closing and this is sharper closing. This is not closing, this is the pulse, right, and rising closing, and then this is sharper closing, right. So, because of that you can able to see that this is the glottal pulse, right, and so this is a glottal pulse waveform, right, and so this, by analyzing this glottal pulse waveform, you can able to see what is the open phase, what is the closed phase, how the closed phase is happening, how rapid it is. So, all these things you can able to analyze this particular signal. And the next one is the LP spectrum for different LP orders, right. So, we have analyzed that in a theory class, we analyzed that. So, this is your voiced segment, this is your voiced segment, and on this voiced segment, now here this plot, what it shows here is that by varying the LP order, for different amounts, how the spectrum looks like. So, this is your voiced segment, and now this is the LP spectrum. Let us see what is the order. LP spectrum corresponds to the order 14. The first one is that LP spectrum corresponds to order 14, where you can able to see that there are 3 dominant frequencies that are observed over here, right, 3 dominant frequencies that are clearly observed over here. This is the first one, second one, third one, and there is a small thing is there over here, it is observed, right. So, there are 3 dominant frequencies with the order 14, and now you can see the next one is that order 10, and here when you perform the LP analysis on this voices segment with the order 10, the spectrum, the LP spectrum that will be captured will be something like this. The LP spectrum that is captured will be something like this, almost like very close to this one, and here with LP order 14 you can able to see the peaks more sharper, more clearer, whereas here the peaks are slightly broader, the made broader, and here in both the cases you can see the locations of the peaks, they are almost same, because here the order is 10 here and then the above one is order is 14. So, there are sufficient order of the polynomial, so with which it can able to derive the corresponding formant frequencies very well, because as we have seen in the LP analysis, like a quadratic polynomial will results to be a peak or a 0, or with results to be like a complex pair of complex conjugate poles, and this pair of complex conjugate poles will provide the peaks in the spectrum, because the polynomial is in the denominator, it is all pole filter. So, therefore, if you want to have the complex conjugate poles, right, so that means the order of the polynomial will be quadratic polynomial. So, therefore, each quadratic polynomial or each factor of quadratic polynomial may give you the complex conjugate poles, and this pair of complex conjugate pole will try to provide you the peaks, the formants. So, since it is a 14 and 10, we have sufficient order is available. So, with that the formant frequencies, the 3 or 4 formants, whichever is very dominant, so they can able to stand out, that can able to be observed from the LP spectrum. And the next one is that here you can see this is the LP spectrum. If you consider the order in the analysis is 6, you can see if you consider the LP order 6, you can see here it derives only the 2 peaks, 2 formant frequencies, because the order equals to 6. Out of this the 6th order polynomial, you can you can get the at most the 3 pairs of complex conjugate poles. Here in this, it may so happen that it has been given only 2 complex conjugate pairs and then another may be real poles. So, because of that, you can see that only 2 formant frequencies or the 2 dominant frequencies are observed. And here in these 2 dominant frequencies also, if you look at here, as the order is reduced, you can see that the peakiness or the shortness of the peaks are not much observed, or instead the peaks appears to be very broader. You can see here at the 14, you can see the peaks are very short, right, and here the peaks are gradually become broader and broader. You can see when the order equals to 6, instead of 3 formants, 3 peaks, we are observing only 2 peaks, that means we are missing 1 peak, or other way you can say that instead of these 2 peaks, it is giving the peak in between, but that is not the right one here. Instead, actually here, because here we are not giving a sufficient order, so therefore, what it tries to give is that for these 2 peaks together, it is giving only 1 dominant frequency. That means, instead of giving the 2 peaks with a higher resolution, what is giving these 2 peaks, the mixed version, it is giving as a peak that is in between this. That means, it is showing that the dominant frequency is here, like that means the total thing, these 2 peaks are mixed and then shown as a 1 peak. And here anyway, this peak here is there, you can have this peak, it is not at all showing as a peak. Here detecting the peak here in this case will be difficult, because it almost appears to be like very flat, because this is also missed out. So, therefore, the order 6 and lower orders and all, where you may not get the spectrum accurately, or you may not provides the dominant frequencies or the formant frequencies very effectively. That is what you can able to see with order 4. You can see that the order 4, the next one is order 3, sorry. With order 3, you can see only 1 peak is observed here and there is no other peaks, whereas here you can able to see some trace of the second peak, but here even that is also not observed, right. And then finally, if you look at the order 1, it means that you are considering only one previous sample, that means only one AK is observed. So, therefore, you can see there is no peak at all, it is like exponentially decaying, because there is only one coefficient, means it is a linear factor, right. The polynomial contains the order 1, that means there is no question of complex conjugate poles. So, it is a real pole, right, you will get a real pole. So, with a real pole, how the spectrum will be? The spectrum will be something like this. You can see it is very loose or very gross level of the spectral envelope, that means there is no details about the spectrum are observable. So, therefore, from this analysis you can able to see that now for a given voice segment we have analyzed the LP spectrum, the characteristics of LP spectrum for different orders, right. So, we started from 14, suppose instead if you start from much higher like order of 30 or order of 25, you can see that the envelope may be there, but no, you can able to observe some spurious peaks also, but that is also not desirable, because in a given speech spectrum these are the 3 dominant frequencies, right. But if you give a more order, then it tries to push the ripples also as the dominant places or dominant peaks, and that leads to again difficulty in extracting the formants properly. But here in this case you can clearly note down that actually these 2 are the dominant formants and afterwards this is a dominant frequency, right. So, 3 dominant frequencies can be observed here, whereas if you perform the LP analysis with order 30, where you can able to see some spurious peaks, unnecessary peaks also will be observed here, here, here and so on. It means that the ripple characteristics also will be popped up or will be shown up here in the LP spectrum, but that is not desirable. So, therefore, for analyzing the voices segment, the desired LP order will be like order of like in between 10 to 15 or 10 to 14 or like 8 to 15, 8 to 10, 8 to 12 is the reasonable one. If you go lower side, that means for order of 6, 4 and so on, you can able to see that the spectrum will be very like smooth. You don't you don't observe the formant frequencies, right. If the order is very high, then again it is a problem, you will get a spurious peaks. So, that is the problem with the LP order. The same thing here now we will see that how the LP order affects on the error signal. Here you can see this particular plot, see. So, it is the LP order on x axis and this is normalized error. So, when you perform the LP analysis, that means the magnitude of error by varying the LP order, you can see that when the LP order equals to 0, it means that we are not when the LP order equals to 1 or 0, right. So, it means that actually there is no history at all. So, therefore, we have to put the random guess. So, therefore, the maximum error is observed when LP order equals to 0. Then as you increase the order LP order, you can see that, right, you can able to see that the error will be decreases, right. In case of voices segment, the error will be decreases very drastically, and in case of unvoiced segment, since the speech segment itself is a random, there is no correlations. So, even though if you take a prediction, if you take a past samples also, the prediction will be poor. So, therefore, it results to be more error and all. So, if you look at for unvoiced segment, even if you increase the LP order beyond 14 also, the error will be come down to only 80%, like, and whereas for voice segment the error has been come down to like 10% of the maximum error and all. So, therefore, it means that because the correlations are there in case of voice segment, so therefore, the prediction will be better. So, therefore, as you consider more and more samples of as a history, the preceding samples, you will get a better prediction. But you can see here from this, you can able to see the error will be reduces like drastically up to 8, and afterwards the reduction error is not significant. So, from this way also you can say that the linear prediction order 8 is reasonably good, 8 to 12 is reasonably good, and beyond that the error is not much reducing. So, from the viewpoint of error, you may consider the higher order, there will not be any problem at all. But if you take higher orders, when you are estimating a spectral envelope, you will get a spurious peaks, and that leads to erroneous results and all. So, that is the problem with the taking the order to be like we have to take a proper order. LPA order is nothing but proper value of a P, so that both the spectral estimate and the error will be minimized. The spectral estimate will be better, and as well the error also will be the minimized in a decent way, right. And yeah, this is about the linear prediction analysis, and like with which you can see whatever we discussed in the class. So, those things you can able to observe here, like how to perform LP analysis, and then what will be the linear prediction residual in case of voice speech and unvoiced speech, right. And how do we analyze the error with and then what will be the order, the effect of LP order on the estimation of spectrum, and as well as the estimation of the error also. All these things we have observed over here. So, we will stop here, and in the next class we will start the next topic. It is a vector quantization. So, so far when you are discussing about speech processing along with these theory lectures, for better understanding, so it is better to conduct some basic speech experiments with which one can able to get a better feel and hands-on experience on the dealing with the speech signals. So, in view of that, I suggest to visit the website at IIT Hyderabad, where they have like developed 10 experiments on speech, and they are available in the form of virtual lab. And so, you can visit this website and you can download those experiments to your local machine, and you can able to practice on your own. And here the clear directions are given, and you can please go through that, and you can able to practice on your own, and with which you will get a clarity on whatever you are discussing in these theory lectures. You will get a better clarity and better understanding of the contents whatever we are covering in these video lectures and all. And here in this context, I want to introduce the two more speech analysis tools that are publicly available in internet. So, one of them is a wave surfer and other one is the PROT. So, these two tools, the speech analysis tools that are available in the internet at these URLs, you can able to download these two from these by accessing these URL, and you can download to your local machine, and then you can able to practice. So, by using these softwares, by using this speech analysis softwares, you can able to capture the speech signals, you can able to display the speech signal in time and frequency domain, and also you can able to visualize the various characteristics of a speech signal such as spectrogram, the pitch contours, energy contours, and so on. Okay, thank you.